Okay, so continuing on with lesson 4.3, let's start out with these. We've got a couple properties that we need to talk about. The first one is if you just have this constant value here being multiplied, it's like a coefficient to some function right here, that can be brought out front and then multiplied in the end times that function. The other rule is that if you have an integral of some piece plus or minus another piece, those can be separated up into separate integrals. You can find them each individually and then add them together or subtract them depending on what you're given. All right, so here's a good example of all of that. So this first one, this gives me a lot of information right here. So I'm going to match it up to what they're trying to get me to find. They want me to find this integral from 2 to 4, and if you look, these are all 2 to 4, 2 to 4, 2 to 4, right? So I'm talking about the same interval. Then this piece of my function right here is actually given to me right here. They told me it was 60. So they're telling me that this piece right there is 60. So if I separate that out like this rule up here told me I could, then I already know that that much of it is 60. I don't have to find it myself. This one is very similar to this one. So let me tell you how. Let me go ahead and separate these up. So my first one is x to the third. I have it exactly right there. My second one, this is actually minus my 3 times x. I could rewrite that as 3 times the integral of x dx. I forgot my dx on that one. So this piece right here, the reason why I did that is because that piece is right here. They told me it was 6. So I'm going to be able to just put that there, but I have to take 3 times that. So that 3 that I put out front gets multiplied. Plus this last one, I'm going to do 7 times the integral from 2 to 4 of just dx. Why? Because I have the integral of dx right here. It's 2. So I'm going to have to just do 7 times 2 right here for this one. All right, so let me write those out. So this one is exactly 60. They gave that to me. Minus 3 times whatever this one was. It was 6. Plus 7 times whatever this one was, which was 2. All right, so that means I have 60 minus 18 plus 14. And if I get all that added together or subtracted, I end up with 56 units squared. I forgot that little piece. All right, this one, I'm going to have to actually do something with it, but it is pieces again, so I need to think about each of those pieces like I did on that one on the other video. So let's look at these split equations here. So the first one, first of all, I'm going from 0 to 4. That's the interval I need to look at. So I'm just going to kind of remind myself of that. I'm going from here to here. So that's really all I care about. Everything outside of that means nothing to me. So this first one, my function is y equals x plus 4, or f of x equals x plus 4. So that means I have a y-intercept of 4 and a slope of 1, and that's for everything that is less than 2. So right here down is what I'm looking at. So slope of 1 means it's right here, and all the way up to that point, but not including it because it's not equal to, and then everything this direction. So here's that equation. The other piece is, okay, I'm going to go back. The same thing happened on that last video. I need to count in a different interval because my y-intercept on this one is 16. I am not going to go all the way up 16. So instead, let's count by 2s. 2, 4, 6, 8, 10, 12, 14, 16. That's a little bit better, right? So on that first one, it was 2, 4. And then up 1 over 1, so I got to be a little bit careful there because I'm still counting on my interval. So this is actually an open circle right there, not a closed. Fix that a little bit. My eraser's terrible. Okay, so here's my new line. And then I'm going to do my second one at 16. That was right here. And I'm going down to over 1, down 2 over 1. And remember, that's only true for 2 and up. So down 2 over 1. And I'm going to go this direction. Okay, now remember, I only care about this piece right here and this piece right here. So I'm going to do those two separately. So I've got a trapezoid for each of them. So my areas are going to be 1/2 base 1 plus base 2 times the height. Same thing for the other one. 1/2 base 1 plus base 2 times the height for each of those two trapezoids. So my first trapezoid, 1/2. My base 1 and my base 2 are here and here. This time, remember I counted by 2s. So this one is 4, this one is 6. 4 plus 6, and then this is as is, that was 2. Okay, and then this one, base 1 and base 2, I definitely have a height of 2, so I'm going to go ahead and put that there, but my base 1 and base 2 was 2, 4, 6, 8, 10, 12, and 2, 4, 6, 8. So I have 12 and 8 for my two bases. All right, so that gives me half. Actually, I'm going to cancel that out. Why not? So that really just gives me 10. Plus this one, that cancels out also. 12 plus 8 is 20. So that means my overall area is 30 units squared. Okay, so then I have something called the trapezoidal rule. This is where a lot of people are like, whoa, what are you talking about? So trapezoidal rule, trapezoids are a lot more accurate when finding areas under a curve than rectangles were. So remember we had these curves and we were like, let's find all of these rectangles in here, right? Well, if those were perfect rectangles, there was like this, either this overhang or maybe it was under, right? And there was something missing right there. But if that was a trapezoid, then it's a lot more accurate because then you can do that at an angle and it's going to be a lot less that's missing or hanging over. All right, so here's our trapezoidal rule. B minus A over 2n equals this funky stuff. So here's what I want to point out to you. This is just the function at that point. This is 2 times it, 2 times it, 2 times it. All in the middle is doubled. And then this one right here is just another single. Okay, now in class we can talk more about what that means. So maybe during a Google Meet I can show you why this is the way that it is. I think your book might have a proof of that. It's actually very clear. If you just found the areas of a whole bunch of trapezoids, you would know what I mean by that. But I'm not going to do that in the video just for time saving reasons. So, but I am going to show you this example. So I have this integral from 3 to 7, and it's the square root function of x minus 3. So let's look at what that looks like on an actual graph. So the first thing I'm going to do is find my values from 3 up to 7. So I'm going to plug it in other words. So I'm going to find f of 3 all the way up to 7. So f of 4, f of 5, f of 6, and f of 7. So essentially what I'm doing is I'm making an xy table for 3 up to 7. I'm just going to write it like this so I can see it. So if I plug 3 in here, 3 minus 3 is 0. Square root of 0 is 0. If I plug 4 in there, that'd be the square root of 1, which is 1. If I plug 5 in there, I get the square root of 2, which I'm going to write that as 1.4142. I'm going to estimate that. So I just did it on a calculator. Same thing with f of 6. If I plug 6 in here, I get the square root of 3, which is about 1.7321. And then if I do 7, 7 minus 3 is 4, so that's the square root of 4 is 2. Okay, so now I have all of those values. That gives me an idea of what this looks like on the graph. So at 3, f of 3, I was at 0. At f of 4, I was at 1. F of 7, I was at 2, so there's 4, 5, 6, 7. I was right here. And then these two were kind of in between, 1.4 something, 1.7 something, so it goes kind of like this. Okay, so that's what my graph looks like, and I need to find the area from here up to here, and the rule is I'm just going to find a whole bunch of areas of trapezoids in there. Now, they want me to do this in two different ways, so I want you to look at the question up here. One says they want me to do it for n equals 4. The other says they want me to do it for n equals 8. Basically what that means is you're going to have 4 trapezoids or you're going to have 8 trapezoids. If I have 4 trapezoids, it's pretty easy. That means I've got this one right here, which is actually a triangle. This one right here, which is a trapezoid. This one is a trapezoid. This one is a trapezoid. All right, so I'm going to have those 4 trapezoids. So let's do that one first. If n equals 4, then I'm going to do the integral from 3 up to 7 of my function, and I'm going to use my trapezoidal rule to do that. So here's my rule. My rule is I'm going to take b minus a, which in this case was 7 minus 3. So I'm going to do 7 minus 3 over 2 times n. Remember, n they gave me was 4. So this is 2 times 4. Then I'm going to multiply that by f of that first x value. Remember how I found f of 3? That's my first one, so that would be 0 in this case, plus 2 times the next one. So 2 times 1, and then 2 times the next one, so 2 times 1.4142, plus 2 times the next one, which so I'm going to kind of come down here and say 2 times 1.7321, plus the last one is just the function again, not 2 times that. So my last one is just 2. So I kind of did a continuation over here. Sorry about that. Okay, so then I'm going to actually solve that. So 7 minus 3 is 4, and 4 divided by 8 is 1/2. Remember, this is an approximation, so I'm still going to put about. And then I'm going to find all of those values inside there, and I'm not going to write all that out because I already found the answer on a calculator, so I'm just going to tell you what that was. When I took half of all of those added up, I got about 5.1463. So check that on your calculator and tell me if you get the same thing, okay? Okay. The next one, they wanted me to do the same thing. So here's my units squared. Sorry about that. The last one, they want me to do the same thing, except this time n equals 8. Well, if n equals 8, that means I'm looking at this same picture. So I'm still doing this, and then here somewhere, and in here somewhere, and here. So I still have this picture, but this time I need 8 subintervals from here to here. That means I have to do some here at these half marks. So my trapezoids now are inside here. So I have 1, 2, 3, 4, 5, 6, 7, 8 of them, right? So now I have to think about not just f of 3, but I also have to think about f of 3.5, right? So let's write them down here. I need f of 3, which we already found was 0, but now I also need f of 3.5 or 3.5. I also need f of 4, which I already found was 1, and I need f of 4.5. And I need f of 5, which I already know, and I need f of 5.5. And I need f of 6, which I already know, and I need f of 6.5. And I need f of 7. So I have all of my other values. I need these ones in between. So again, I would go on a calculator and I would figure those out. So this one is 0.7071. This one is 1.2247. This one is, oh, I didn't write that one down, so let me go back and find it in a second. 1.8708 is that one. Let me find my other one. I got kind of lazy and just wrote a dot, dot, dot. So let me find it. So how am I finding those? I'm taking these values and I'm plugging them into the equation, which was the square root of x minus 3. So I'm going to do x, which was 5.5 in this case, minus 3, and then I'm going to find the square root of that. So that gave me about 1.5811. All right, so now I have a big thing to deal with right here. So my area in this case is going to be about my 7 minus 3 again, all over. This time it's 2 times 8 instead of 2 times 4, times all of these values. So 0, this one is not times 2. These all are times 2. All of these are times 2. And then this one is not times 2. Okay, so I've got 2 times 0.7071 plus, and I'm going to just do all of those in between there, 2 times all of these things. So let me write my second to last one there. 2 times 1.8708. And then, let me get back in focus. Sorry about that, guys. There we go. And then times my plus my last one, which was just 2. So if I figure all of that in there, that means I'm taking 4 over 16, so 1/4 times all of that, what I get. So 1/4 times all of that stuff. And I ended up in this case with 5.265 units squared. So remember back to our rectangles. The more rectangles we had, the more accurate the answer was. Same thing here. These two are really close to each other, but this one is the more accurate of the two because there were more trapezoids in there.